So we're going to assume that maybe we need to brush up on that a little bit, and this unit will start with us actually just doing a quick review of the factoring strategies you would have been introduced to over the past couple of years of your lead up to pre-calc. All right, so we're going to get started with looking at a review of our factoring strategies. So here are the strategies we're going to go through. We're going to go through greatest common factor, simple trinomials, hard trinomials, perfect square trinomials, and then finally using difference of squares. This is the skill set that will be extremely important that students accumulate. Again, you don't have to be masters of them right now, but by the time you are finished this section and then leading in, because we are going to use this extensively over the next 3 pre-calculus and calculus courses, you must become proficient at factoring. As I said, you don't have to be right now, but it's going to really fall upon you to make sure that you get these methods down and mastered. All right, so let's start with greatest common factor. Greatest common factor, just to review, is where you're looking for the largest possible values in terms of both numbers and variables that divide evenly into every expression, or every term, sorry, in an expression. So if I look at this first binomial here, you'll see it has 2 terms in it. In order for something to be a greatest common factor, it must divide evenly into every term. So if I look at 8, I always look at my numerical coefficients first. So I have an 8 and a 4. You ask yourself, what is the largest possible number that divides evenly into both of those? And it would be a 4. So you write it down. I have an x squared and an x, which means x will divide into both of those. It's always the lowest exponent of any exponent that repeats. So for example, I have x squared and x to the 1. Let's suppose this had been an x to the 4. Well, then the GCF would have been x squared, the lowest. No, it wasn't, so let's get rid of that. So here, because there's an x in every term, and the lowest power of x that's present in any of those terms is x to the first, there's your GCF. So then what you got to do is figure out, well, what would you multiply this by to get both of these back, which in theory ends up to us dividing each of these. Now, we don't actually show this. We do this in our heads, but I'm going to write it out the first one just to show you. You divide each of these terms by the greatest common factor. So 8x squared divided by 4x. 8 divided by 4 is 2. X squared divided by x, you subtract exponents. That'll be x to the 1. 4x divided by 4x. Now sometimes students say, oh, you don't have to put anything. They crossed each other out. No, you have to put a 1. When you divide those out, you get a 1. As a quick check to see if you did it right, now you have accomplished the goal of factoring. I'm just going to back up a second. Often we'll say, okay, well, tell a student factor this. And those students, sometimes students say, I don't even know what he means. It's hard to do something when you don't know what your end goal is. Your end goal of factoring is to take an expression and eventually end up with expressions multiplied together that would give you this value. It's comparable to this. Let's suppose you had the number 12. And in grade 10, we did what was called factorizations or prime factorizations. And you told me, oh, well, that's 6 times 2. I've just factored because I know that this multiplied by this will give me this. If you took the number 6, and it will factor further into 3 and 2. And now once you're down to prime numbers, that's called prime factorization. That's essentially what we're doing here. We took the binomial 8x squared, take away 4x, and we factored it into 2 things, 4x and 2x minus 1, that if I multiply those together, I would get this expression. Just like up here, if I multiply the 6 by the 2, I get the 12. So the goal of factoring is to come up with expressions that multiply together to give you this. And just like up here, you always have to check these factors to make sure that they don't factor any further like the number 6 did. Now in this case, that's a monomial, so it's not going to factor any further. And this binomial doesn't factor any further. So this right here would be my final solution. 4x multiplied by 2x minus 1. All right, so that one we went through in great detail. we'll start speeding things up here and go a little bit quicker now. So now I look at this one. It's a trinomial. I have 12, 9, and 3. They're all divisible by 3. X cubed, x squared, and x. That means they're all divisible by x to the 1. Now divide each of these by 3x. So I'll get 4x squared. Take away 3x plus 1. If I just quickly check, 3x times 4x squared gives me that. 3x times a negative 3x gives me the middle one. 3x times 1 gives me that one. So I know it is correct. I'm going to give a quick look to this trinomial and make sure it doesn't factor any further. Now you'd have to recall some of your factoring strategies from last year, which we'll get to here shortly. This is called a hard trinomial. 4 times 1 is 4, and I've got a negative 3 in the middle. So I'd be looking for two numbers that give me a positive 4 when I multiply them, and the same two numbers when I add them give me negative 3. That's impossible, because the only way to get 4 is 4 and 1, both positive, or both negative, or 2 and 2, both positive, both negative. Neither of those would give me a sum of negative 3. So this one's finished. All right, let's have a look at this one. So I've got 8, 32, and 8. So definitely every term is divisible by 8. I have x only in the first term, so x is not a common factor. I have y to the first, y squared, and another y to the first, which means y is in every term, the lowest power anywhere. There's a 1, a 2, and a 1, so it would be to the first. Divide each of these by 8y. That's going to give me just an x here, 4y here, subtract 1 here. Those two multiplied together would give me that back. So I've just used what's called greatest common factor, often abbreviated GCF. This is an example to show you that your greatest common factor can also be a multiple termed expression. In all of these, our GCF, you can see here, was a monomial, monomial, monomial. But if you look at this one more carefully, you'll see there's an x subtract 1, an x subtract 1, and an x subtract 1 in each of the three terms. So in this case, the greatest common factor is a binomial, x subtract 1. And now if you divide each of these by x minus 1, you'll be left with x squared plus 3x subtract 5. I'll check this to see if it factors any further. It's a simple trinomial. I would have to multiply to get negative 5, and then the numbers that I multiply to get negative 5 would have to add to give me 3. That's impossible. The only way to multiply to get 5 is 5 and 1. There's no way to combine those with positives and negatives to get a plus 3. So you're done. All right, so there's a quick refresher on the first strategy of factoring that you should be familiar with and have seen before, called greatest common factor. Now we're going to move on to trinomials. First, we're going to start with simple trinomials. Now, we'll say this, but once we get going, and I'll even do it myself sometimes, we'll forget about it, but this is important. You should always, always look for GCF first. All right, so even if you see a trinomial and say, oh, look at that, that's a hard trinomial, look for GCF first. All right, so I look here. So what do you mean by a simple trinomial? Well, I think everyone knows trinomial means 3 terms. 1, 2, 3 terms. That's a trinomial. The reason this one's considered a simple trinomial is because the leading coefficient of your x squared or a squared or b squared, whatever squared is a 1. That makes it what's called a simple trinomial. If that is the case, and in fact, now they don't, just because it's a simple trinomial doesn't necessarily mean it factors. Obviously, we're going to pick ones for the most part that do, but not every simple trinomial factors. You put down 2 brackets. If it's x squared, you'll put x and x. Now, here's the thinking that your brain goes through. You look at the last term, positive, and you have to look at the sign as well, a positive 27. You need to find 2 numbers that when you multiply them, the answer is positive 27. Those same 2 numbers that you pick, when you add them, you have to get this number in the middle, including the sign, a plus 12. So then the 2 numbers, when you add them, you have to get a positive 12. So obviously this can be a struggle. Now sometimes I find students at the grade 10 level will struggle more with this than hopefully we run into in pre-calc. But the major issue with some students is they don't know their multiplication facts. They don't know how to quickly come up with the numbers that multiply to give 27. Well, they're supposed to be ingrained in your brain by this point. If they're not, that's going to be an issue. You've got to work on your multiplication facts. 27 and 12, 9 times 3. There's the pair I'm looking for, both positive. 9 times 3 is 27. 9 plus 3 is 12. Now, I don't want to see you writing this out all the time. I want to see you in your brain thinking this, just quickly with some mental math. And then you go to your brackets, you put plus 9 in one bracket, and you put plus 3 in the other bracket. And now I'll show you that this is correct. And you don't have to check this every time. I'm just going to show you how you could. X multiplied by x squared. X multiplied by 3 plus 3x. 9 multiplied by x. 9 multiplied by 3. Add these two together. There you have it. Proof that this multiplied by this would give you back the original expression. So like I showed you before, we have taken a bunch of terms, added, subtracted, and changed it into two expressions that would multiply together to give us this trinomial. Okay, so let's get the brains going here a bit quicker. I need two numbers that multiply to give negative 12. So the only way to multiply and get a negative, as soon as you see this is a negative 12, one of them's got to be positive and one's got to be negative. So I know for a fact one of the numbers is positive, one is negative. The two numbers, when I combine them, have to add to give me a plus 4. All right, so I'm going to go x and x times x, there's your x squared. Now multiply to get negative 12 and add to give 4. So if you say, well, how can I multiply and get 12? 12 and 1, yeah, they don't combine to give me 4. 4 and 3, they don't combine to give me a 4. 6 and 2, ooh, that might work because they differ by 4. Now you got to get the right sign on the right number. So to get a positive 4, you need to have a positive 6 and a negative 2. 6 times negative 2, there's your negative 12. 6 plus a negative 2, there's your plus 4. Factored. Now the next two, I always tell students, are two of my favorite trinomials because these ones, they're a little tricky. Not that the strategy is no different, but you really, really have to pay attention to signs, and there's two pairs of numbers that look like they might work. And if you're not paying attention to signs, you might pick the wrong pair. I'll show you what I mean. All right, so I need to multiply to get negative 24 and add to give negative 10. So when I say there's two pairs of numbers that look like they might work, those two pairs of numbers would be 6 and 4, right? Because they combine somehow to give me a 10. And also 12 and 2. They could maybe combine some way to give me a 10 and also multiply to give 24. Now, to get a negative 24, I would have to have one number positive. So one's got to be plus and one's got to be minus. I know that for a fact. Well, if I tried to use 6 and 4, the only way to get a negative 10 would be with a negative 6 and a negative 4. The problem with that is if I multiply them together, I get a positive 24, not a negative. So they don't work. I'm going to have to use a positive 12 and a negative 2. I'll find lots of examples of students that put negative 6 and negative 4 here. Well, they only looked here. They ignored the fact that they got to get a negative when they multiply these two together. So if I check mine real quick, 12 times negative 2, there's my negative 24. 12 plus negative 2, there's my negative 10. My positive. Oh, I got these backwards. Good thing I talked myself into this one. Because those would add to give me a plus 10, not a minus. So I got these in the wrong place. This should be negative 12, and this should be plus 2. So I'm sure you were screaming at your screen as you're watching me do that, I hope. That works better now. Negative 12 times 2, there's my negative 24. Negative 12 plus 2, there's my negative 10. All right, here's another pair of factors that could have what appears to be multiple factors that work. So I need to multiply to get 30, positive 30, and I have to add to get 13. So the two pairs of numbers that could possibly combine to work would be 10 and 3, but also 15 and 2 differ by 13. Now because this one's positive, I know that these both have to be either positive or negative. Well, because they're going to add and give a positive, I know they have to be plus signs. in this case. Now, if that was a minus, I'd know they both have to be negatives. That's the only way to multiply and get a positive and add to give a negative sum here in the middle. Okay, so to get a positive 30 when I multiply and add to be a positive 13, we're going to have to use 10 and 3. Now you see why, so sometimes students say, why didn't you use 15 and negative 2? See, those work too, don't they? 15 plus negative 2, there's your 13. Here's the problem. 15 multiplied by negative 2 is a negative 30. So you can't just haphazardly ignore these signs. It's really, really important that you look at the signs when you're doing these questions. All right, so those are simple trinomials. Three-termed expressions, leading coefficient is a 1. Yeah, I think just before I go to hard trinomials, I want to show you that factoring is really patterns. And if I was to, I'm just going to put a blank page in here and ad-lib a little bit from your notes. Let's suppose that I had x to the 6th minus 3x cubed subtract 10. Now, this isn't the same pattern that you saw earlier where I had like x squared take away 3x take away 10. I could do this easily. It'd be x minus 5 and x plus 2. Multiply to give negative 10, add to give negative 3. However, if the pattern that we followed here holds like this one does, where it doesn't matter what this exponent is, as long as this one is half of it. So this could be x to the 4th, as long as this is x squared. This could be x to the 10th, as long as this is x to the 5th. The only thing that changes is the exponents on these. They're always going to be half of this or the square root of it. So for example here, I can still factor this using the same strategy. The only difference is you put x to the 3rd and x to the 3rd. When you multiply those two together, you add exponents. That would give you your x to the 6th. I want to get a negative 10, so negative 5, and I want to add to give minus 3. All right, so as long as this exponent is half of this one, and you have this, you can still use the same strategy with that slight adjustment of your exponent on here. So you'll see that from time to time, not real often, but you should be able to manage that if you run into it. And that's where kind of pre-calc ratchets things up a little bit from maybe your basic grade 9 and 10 math, where we just expect those little extras out of our students when we get to this point. Okay, on to a hard trinomial. So hard trinomials are essentially the same layout as the last, with one small exception. The number in front of the x squared is no longer a 1. Now with these ones, you're always going to want to check for a GCF in the beginning, because maybe there's a greatest common factor that will turn it into a simple trinomial. I think I have some later where that happens. So I look here quickly, 2, 7, and 6. Nothing divides into all of them, so I do not have a GCF, which means I am going to have to use a strategy. Now I'm going to show you two strategies, just so that you see them, because the first one I'm going to show you is called decomposition, and the second one I'm going to show you it's called the Australian method. Now I've seen this one called other things as well, but that's what I've seen it called when I researched it a little bit on YouTube. Okay, so let's go decomposition first. This is how decomposition works. Now they're both essentially based on the same type of logic in the beginning. You always take the number in front, it's called the leading coefficient, and you multiply it by your last term, including the sign, so 2 times positive 6, and you get a positive 12. You now need to, like a simple trinomial, find two numbers that multiply to give this, not this one, the plus 12, and they add to give the middle term. So that would be 4 and 3. Now, what students do wrong is they want to go right to the answers like they do with simple trinomials. Doesn't matter which strategy you pick, hard trinomials involve multiple steps. You don't go right to the answer. So here's my middle step. I'm going to go 2x squared, and this is where it gets the name decomposition. I'm going to split apart, decompose the middle term into the two numbers that I've come up with, 4 times 3. And you're going to write, instead of plus 7x, you're going to change it to plus 4x plus 3x plus 6. And then this is going to lead us to another type of factoring called factoring by grouping. It's where you, rather than factoring across the whole thing, and it usually works nice if you have 4 terms, you're going to take just the first 2 and then the second 2, and you're going to do greatest common factor. So looking only at the first 2, you take out 2x, leaving you with x plus 2. Now you're going to look at the next 2 and say, what's common to those? A positive 3. If you divide these both by positive 3, you get x plus 2. Now here is your indicator of whether you're on the right track or not. It's these binomials. If those are different, you've picked the wrong numbers here, or you factored out something wrong, they have to be identical. Signs, everything's got to be the same, which they are in my example. So then you take out that binomial as a GCF, so it comes out to the front. So if you divided the first term, consider this all the first term, by x plus 2, you'd be left with the 2x. And if you divided all of this by the x plus 2, you'd be left with a plus 3. X times 2x, there's your 2x squared. X times 3 is 3x, 2 times 2x is 4x, 4x and 3x, there's your 7x, 2 times 3, there's your plus 6. That's called decomposition. So if you like that, roll with it. A lot of people have, when I first learned this in my school, high school days, this was the only one we were shown. So I always did it this way until probably about, I don't know, the last 3 or 4 years. Mrs. Much ran across this method somewhere and showed it to me, and it works probably a bit quicker. I would say I use this now probably about 99% of the time, and I'm not saying which one you have to use. Again, I like to show you both, and I like you to pick the one you're more comfortable with. Now, here's how this is how the Australian method works. So it's still the same thinking. You multiply, you get your 12. You need 2 numbers multiply to give 12, add to give 7. That's all the same. This is where it's different. It starts out like simple trinomials. You put 2 brackets here. If it's 2x squared, you put 2x at the front of this bracket and 2x at the front of this bracket. So you basically leave the leading coefficient, whatever it is, and you take the square root of your exponent. Now, the 2 numbers that we come up with were 4 and 3. So in one bracket, you're going to put one of those numbers. In the other bracket, you're going to put the other. So a common mistake is students do this, and then on they go to the next question. You're not finished. As I said, there's always, even if you use the Australian method, there's still more work to get to the final answer. We know this is the final answer here. You can see this isn't. I can see clearly this doesn't work because 2x multiplied by 2x doesn't give me 2x squared. It gives me 4x squared. Here's what will always happen. At least one of the brackets will have a greatest common factor in it. Sometimes both. In this case, just the left bracket. It has a GCF of 2. The right bracket, there's nothing that divides into both of these. Now, this is where it's a little different. We don't actually factor it out to the front. We physically divide each term by the GCF. 2x divided by 2 is just x. 4 divided by 2 is 2. This one doesn't have a GCF. It just stays the way it is. Now look at where we ended up. Same place. X plus 2 multiplied by 2x plus 3. So this is Australian method. This is called decomposition. I'll probably, every once in a while, I'll just kind of change things up a little bit and do one or the other. We want students to have what's called number sense, so that if they see me doing it this way, and they walk into a room in 3 years' time and a professor at the front of a university room is doing it this way, they'll understand what's going on. They understand both methods. All right, now we go to our next hard trinomial. So I'm going to go 3 multiplied by negative 10. Now you can either put that in your head. Personally, I like to, when it's a hard trinomial, just write that number up there. I'm trying to figure out 2 numbers that give me negative 30 when I multiply them. And when I add them, I have to get the number in front of this one, which is a 1, negative 1. Well, if you're adept in your multiplication facts, I think we all agree it's 6 and 5. Now I have to get the right sign on the right one. So I'm going to go Australian method. 3x, leave room, 3x, leave room. So to get a negative 1 when I add them, and a negative 30 when I multiply them, I'm going to use negative 6 and a positive 5. Remember, this is a middle step. It's not the final answer. Both of these are now divisible by 3 in this bracket. And remember, you're only looking within a particular bracket for a GCF, because students say, yeah, but it doesn't go into these ones. We don't care. We're just looking at in each bracket. And you have to check both. Sometimes students think, well, there was a greatest common factor here, so that means there's none here. The first two examples, yes, that was the case, but you will run into examples later where both of these have greatest common factors. 3x divided by 3 is x. 6 divided by 3 is minus 2. This one didn't have a GCF. There we have it. If I was to expand that out, I would get that back. That is called hard trinomials, and that's using Australian method. I got one more here. 12 multiplied by a positive 6 is a positive 72. I want to multiply to get a positive 72, and I want to add to give a negative 17. I'm going Australian method again. 12x, 12x. Let's think. 72. How about 9 and 8? That would work nice. Now, to get a negative 17, I need a negative 9 and a negative 8. And that would work because if you multiply two negatives together, you'll get your positive 72 that you need. And if you add those two negatives, you'll get your negative 17 you need in front. So here's an example where if you look at these brackets, the first one is divisible, both of them by 3, and the second one, they're both divisible by 4. So I have to divide both brackets out. 12 divided by 3 is 4x, 9 divided by 3 is 3. 12 divided by 4 is 3x, 8 divided by 4 is 2. I always say at the very least, check the first two to make sure you have a chance to be right. You say, what do you mean by that? Well, if I multiply 12x and 12x, clearly it's not 12x squared, it's 144x squared. But if I multiply my first terms now, at the very least, I've got that right. It's 12x squared, so I have a chance to be right. You can check the last two. Negative 3 times negative 2 plus 6. So my only other issue is, well, what about the middle ones? Well, 4x times negative 2 is negative 8x. Negative 3 times 3 is a negative 9x. Add those together. Yep, it works. So I know that I have it right. So there is a nice strategy you can use to factor hard trinomials. Continue on our journey of trinomials. Now we're going to look at perfect square trinomials. We've actually already looked at these a little bit because when we did our vertex form and we did completing the square, we were making perfect square trinomials. So we've had the discussion on, well, what is a perfect square trinomial? And if we can pick them out, then we should be able to factor them pretty quickly because we already did it when we did completing the square. Well, the giveaway here is the nature of these. 9x squared. Your brain should say, oh, wait, perfect square. Positive 16. Well, wait a second, that's a perfect square. Maybe this is a perfect square trinomial. Let's do the final check on it. Final check is when you take the square root of the first, again, I'm writing it out here, you can just do it in your head, and the square root of the last one. You multiply those together, you get 12x, double it. Do you get that number? Don't worry about the sign for these ones. Do you get a 24 is all I'm worried about. 3x times 4 is 12x, doubled 24x. This is a perfect square trinomial. If it is a perfect square trinomial, you'll remember me saying this as we did it back in the section on completing the square. You take the square root of the first term, the sine of the middle term, and the square root of the last. Put it in brackets, don't forget the squared. If I just quickly undo this, so go the other way, expand it, remember how to square a binomial, our three-step rule shortcut? Let's just check this real quick to make sure it works. Square the first, multiply together, you'd get negative 12x, double it, and then square the last one. It works. So this is kind of the reverse process. All right, let's check this one. Ooh, look at this one. Something I noticed here. 16, and 4. Before I even get started, I notice they're all divisible by 4. Now, this is what students will sometimes do wrong. They'll actually physically divide these all by 4. I'm not doing Australian method. I need to, in this case, factor out the 4 to the front. That'll leave me with 4x squared. Take away 4x plus 1. Well, good news is this is still a perfect square trinomial. Let's check it. 4x squared, that's a perfect square. Its square root is 2x. 1 is a perfect square. Its square root is 1. 2x times 1 would be 2x doubled 4x. Yes, it's a perfect square trinomial. So we're going to go leave the 4 out there. Square root of the first, sine of the middle, square root of your third term, in brackets squared. So if you expanded this out and then multiplied every term by 4, you'd get this back. Now, just to show you, this is what will happen sometimes. Students might say, oh, I didn't see the GCF. Well, you can still get to the right answer because this was a perfect square. This was a perfect square. The square root of that was 4x. The square root of that was 2. Multiply them together, you get 8x doubled, you get 16. So it does meet the criteria of a perfect square trinomial. So sometimes a student may have missed the GCF and said, well, the square root of this is 4x. The sine from the middle, and then the square root of this one is 2 in brackets squared. Well, if you stop here, you can see it's not the same as this, and it's not correct. Unfortunately, if students miss the greatest common factor here, in my experience, about 95% or more of the time, they don't pick it up here either. But I notice and say, wait a second, these both are divisible by 2. I'd have to factor that 2 out. Now, this is where it gets a little tricky if you miss it in the top line. You take out your 2, and you've got 2x minus 1. So this is the same as 4x minus 2, but you'll notice that that whole thing is squared. So you'd have to put a square bracket around this, and it would be squared. So that's the same as 4x minus 2 squared. But now if you want this to turn out to be this, well, the 2 is going to get squared to give me my 4, and then you just put your squared on that, and now they're the same. I'm not going to disagree. It's more difficult to manage this if you miss the greatest common factor in the beginning. And that just reinforces what I said earlier. Always look for GCF first. Makes your life easier. All right, we got another one here. Let's double check this one. So these are some ugly numbers, but and almost any time you have ugly numbers like this, these big ones, and especially when you get your perfect squares here, it's probably a perfect square trinomial, because if you were trying to get into a hard trinomial decomposition or Australian method on this one, you're going to have huge numbers to be trying to manage. It usually means there's some shortcut that you're missing. Well, 49x squared, 7x, 625 is 25. 7 multiplied by 25 is 175. And if I double 175, I do get 350. We're in business. It is a perfect square trinomial. Square root of the first, sine from the middle, square root of the last one, in brackets squared. Nice and easy as long as you see the pattern. And that's factoring is all about pattern recognition. You have to recognize patterns, and once you recognize the pattern, it'll hopefully activate a strategy in your brain. And as I said, you don't have to be experts at it right now, but by the end of this course, you have to be really, really close to an expert in factoring. It's a critical skill in pre-calc and calculus courses. All right, on we go to our last one, difference of squares. Personally, I like to think this is probably the easiest one of them all. Certainly should be the easiest one to pick out. It is used when you've got two terms. So it's not for trinomials. So right away I see two terms. When there's two terms, you really only have two options, GCF or now this one called difference of squares. Well, the word difference means subtraction. This is used when you've got two terms subtracted, and it works really nice when they're perfect squares. 4x squared, take away 25. They are both perfect squares, and I'm taking the difference of them. There is a nice little shortcut strategy that you can use to factor them called difference of squares. If you forget, this is how it works. You take the square root of the first term, subtract the square root of the second term. And then you take the square root of the first term, and you add the square root of the second term. Now there's a fancy name that maybe you've heard. If you haven't, you should be aware of it. They're called conjugates. We'll use that term a few other times throughout this course. Conjugates are binomials that are identical with the one exception of the sign between them is opposite. 2x plus 5 and 2x minus 5 are considered conjugates. If you expand these out, 2x times 2x, 4x squared. Now here's why conjugates are your two factors here. Watch what happens when you do your middle terms. 2x times 5 is a positive 10x. Negative 5 times 2x is a negative 10x, which wipe each other out. And then you got your minus 25. So the x term gets wiped out anytime you multiply conjugates. Nice little fact to know. 36x squared, subtract 64. 36 and 64 look like they probably have a GCF first, so let's start with that. They both divide by 4, I would say. So 4, that'll give me 9x squared, subtract 16. These are still the difference of two perfect squares. So the 4 will stay there. Take the square root of the first, subtract square root of the second, square root of the first, plus square root of the second. Nice and easy. Difference of squares. All right, a couple more. We'll just have a quick look here. Now, with exponents that are higher than 2, when you take the square root of an exponent, so the square root, let's say, of x to the 6th, it would give me x to the 3rd. Now, students will get thrown off by one like this. If I said, what's the square root of x to the 16th? What do you think? So the correct answer is x to the 8th. And I think you could probably guess what students do incorrectly. They say, why isn't it x to the 4th? Which, of course, they're thinking that because they say I took the square root of 16. It says take the square root. It's not the square root of 16, it's the square root of x to the 16th. And what you'd be expected to recall from grade 10 is when you did some exponent work, the square root of x to the 16th square root can be interchanged with the exponent 1/2. Cube root is the exponent 1/3, fifth root 1/5, etc., etc. When you have an exponent raised to an exponent, you multiply those two together. X to the 16th raised to the half, there's why you take half the exponent, not the square root of the exponent. So it's really, really important. So if you get into education at some point, this is a terrible example right here to start with. I didn't start with it because if you did the square root of x to the 4th, right, and I wrote down here it's x squared, well, some student sitting in the room who's kind of not catching everything could say, oh, I see what he did. He took the square root of 4 and got a 2. No, that's not really what I did. I took half of 4, and that's why I got 2. So if you only ever showed an example with x to the 4th, well, then the students wouldn't know whether you took the square root of it or half of it because you get the same answer. So that's why trying to show students how to do square roots of exponents, stay away from 4. It's a bad example to use. All right, so let's go back over to here. And now, so the only thing you need to know is for an exponent to be a perfect square, you have to be able to take half of it. So I can take half of 6 and I can take half of 8. I'm good. Now students will get looking at that and say, oh yeah, but 6 and 8 aren't perfect squares. They're not, they're exponents. Remember, you're taking half the exponent, not the square root of the exponent. Therefore, this is a perfect square, subtract a perfect square. Difference of squares. Square root of the first, subtract square root of the second, square root of the first, plus square root of the second. Conjugates. All right, here we have another one. Tighten this up a little bit. So I got x to the 4th, subtract 81. Difference of squares. X squared, take away 9, x squared plus 9. Now I think this is the first example of something I mentioned earlier in our presentation. When I showed you an example of prime factorization where I took 12, let's say, and I said 12 is the same as 6 times 2. Well, then you have to check these and make sure they don't factor again and say, oh yeah, well 6 does. It's 3 times 2. It's the same with polynomials and factoring. X squared take away 9, x squared plus 9. You need to look at each of these individually and say, would they be able to factor any further? Well, hopefully this one jumps out and says, hey, wait a minute, that's the same pattern I just did. It's difference of squares again. So you'd have to factor it, x subtract 3, x plus 3. Now then you'll get all kinds of crazy things students will do with this one. But this is the sum of two perfect squares. This is the last factoring strategy on the list. There's no factoring strategy called sum of squares. It doesn't factor. It's like the 2. It's already factored as far as possible. Just leave it the way it is. X squared plus 9. Now you do have to rewrite it. So if you expanded these 3, multiplied the 3 together, you would get that binomial back. All right, so that was one that had multiple layers of factoring. Now, I have a practice sheet. It's in your class notebooks. It's indicated factoring review. So if you'd like to brush up on this and make sure you do get these mastered, certainly open up that sheet and have a look at it. Where factoring becomes a bit more of a task is it's okay when I tell you that they're different to squares and there's a bunch of examples, and I tell you it's a hard trinomial and then I give you a bunch of examples. The key is for you to look at the pattern without any indication of what strategy it is and figure out what strategy that you'd have to use. So here would be an example where I would encourage you to pause the video, have a look at these examples and see if you can factor these. How many do I got? I got 4 of them here. So factor these 4. So there you are, you can see them all. If you pause the video, you can look at them. And now I'm going to go through my solutions. All right, so I look at this first one, and the first thing I see is greatest common factor because there's x's in both of them. So I'm going to take out the GCF, always the lowest exponent, so x to the 5. When I divide both of these by x to the 5, I will get x to the 8 minus 1. Now, this is where we're going to challenge you. This is a monomial, so it doesn't factor. But this binomial is difference of squares. I need to factor that further then. X to the 5th is going to stay as it is. Difference of squares. X to the 4th, subtract 1. X to the 4th, plus 1. Uh-oh, still difference of squares. Keep going. X to the 5th, x squared, subtract 1. X squared plus 1, so that's difference of squares on this one. Now this is sum of squares, so that doesn't factor. Unfortunately, you're still not done. This is difference of squares again. X to the 5th, x take away 1, x plus 1, x to the 4th plus 1. Now you're finished. This difference here is no longer difference of squares. So there was an example where you had to do GCF in the beginning, and then 1, 2, 3 layers of difference of squares before you finally get at your factors. Okay, let's look at B. Let's see what I got for a pattern here. I see a simple trinomial. I need to multiply to get negative 30, and the two numbers I pick, when I add them, I have to get 13. Now, don't be tempted by 10 and 3. They are tempting, but they won't work, because one's got to be positive and one negative to get negative 30. You need to use 15 and negative 2. X plus 15, x take away 2. Multiply, you get that. Add, you get that. Simple trinomial. Next one, hard trinomial. Multiply your 3 by your negative 8, you get negative 24. So I need to multiply to get negative 24. The same two numbers got to add to give me 10. Again, 6 and 4 are tempting, but to get them negative 24, one's got to be positive and one's got to be negative. That won't give me a 10. We're going to have to use 12 and 2. I'm going to go Australian method. So 3x, I'd need a positive 12 and a negative 2 to add to give me 10. This first bracket, they're both divisible by 3. Second one doesn't have any GCF, so it's x plus 4, 3x take away 2. Let's see what we're dealing with here. 27, 36, and 12 are all divisible by 3. Let's take out a 3 and see what that does. So I take out a 3. I get 9x to the 16th plus 12x to the 8th, y to the 18th, plus 4y to the 36th. And this looks like it could be a perfect square trinomial. Let's check it. So the square root of this would be 3x to the 8th. Remember, take half the exponent. Square root of this would be 2y to the 18th. If you multiplied those and doubled, you would in fact get the middle term. So this is a perfect square trinomial. Square root of the first, sine of the middle, square root of the last one. Don't forget to put it in brackets, squared. All right, so that is our refresher, or maybe an intensifier. Probably maybe I didn't tackle factoring at that level in